comets don't imitate each other. They follow their own orbits shaped by gravity, solar heating, and the physics of escaping gas and dust. That's why astronomers were caught off guard when Comet C 2025 R2 SWAN began showing a tail and jet pattern that looked strikingly similar to the interstellar object 3I Atlas. The resemblance alone would be odd. What makes this story harder to ignore is the timing and geometry. Right now, these two comets occupy opposite sides of Earth along the ecliptic plane, the main orbital disk of the solar system. From our vantage point, they form a near-symmetrical arrangement that is difficult to dismiss as a routine coincidence. Here's what we're actually seeing. Two comets, both active, both developing unusual sunward-facing structures, and both appearing in positions that bracket Earth's orbit. Orbital mechanics can produce alignments, but alignments with matching anomalies invite closer scrutiny. At minimum, we're looking at a rare natural coincidence happening in real time. At maximum, we're facing a puzzle that forces us to test explanations we normally wouldn't even consider. Let's name the objects clearly. 3I Atlas was discovered on July 1, 2025 by the Atlas survey system in Hawaii. Once its trajectory was computed, it was immediately classified as interstellar. Its orbit is hyperbolic, meaning its eccentricity is greater than 1. That tells us it has never been gravitationally bound to the Sun. It came from interstellar space at high speed, will pass through the inner solar system once, reach perihelion on October 30th, 2025, and then leave forever. This makes it only the third confirmed interstellar visitor after Oumuamua in 2017 and Borisov in 2019. Comet SWAN was detected later on September 11, 2025, initially flagged by the SWAN instrument on the SOHO spacecraft. Its first classification was ordinary, a long-period comet likely originating in the Oort cloud. Objects like this have extremely elongated but closed orbits. They return to the inner solar system after long intervals and usually behave in familiar ways, brightening as they approach the Sun, growing a coma, forming a tail that extends away from sunlight. But SWAN didn't stay ordinary. Its brightness rose quickly, moving through magnitude levels faster than early models predicted. Observers around the world began tracking it, and with that came the first reports that SWAN's visible structure looked unexpectedly similar to 3I Atlas. Both objects showed extended comae, prominent tail components, and jet-like emissions oriented in ways that don't fit the simplest comet diagrams. The similarity is being reported while the comets are on opposite sides of Earth's orbit, which adds a second layer to the question. Not only why they look alike, but why this is happening now. Before leaning into any dramatic interpretation, we need to be disciplined about what is observation and what is narrative. The data that triggered the attention comes from real images and repeated measurements, not from a single viral frame. Still, similarity in appearance is not proof of a shared origin or common cause. Comets are messy systems. Their comae and tails are sensitive to multiple interacting forces: solar radiation pressure, the solar wind, rotation of the nucleus, and the specific mix of volatile ices inside the object. Even small differences in any of these variables can change how a comet looks from Earth. At the same time, certain combinations of variables can produce similar projected shapes, even when the underlying physical reality is different. That's why the first serious step is orbit geometry. Orbital elements don't care about interpretation. They tell us where an object has been and where it is going. For 3I Atlas, every line of evidence points to an unbound visitor. Its hyperbolic orbit, high incoming velocity, and approach direction show it is not from our solar system. It is passing through. That alone is important, because interstellar comets are rare and carry chemistry shaped by environments beyond our own. SWAN's orbit tells a different story. Its eccentricity is about 0.994, very close to 1, but still less than 1. That means it is bound to the Sun on a long, closed ellipse. It likely spends most of its orbit thousands of astronomical units away, in deep outer space, and only occasionally returns inward. One full loop takes centuries or longer. Its perihelion distance is about 0.5 AU, roughly half the Earth-Sun distance. That is close enough for strong heating, vigorous sublimation, and bright activity, exactly what we expect from a typical long-period comet approaching the Sun. So the orbital math gives us a clean separation. One comet is an interstellar traveller on a one-time hyperbolic passage. The other is a solar system native on a long return orbit. Their orbital planes also differ. If you map the solar system from above, 3I Atlas comes in on a steep trajectory relative to the ecliptic, while SWAN follows a more standard long-period path, aligned closer to that plane. Rewind their paths through time, and they never converge. There's no plausible moment where they shared a parent body, crossed the same region of space, or fragmented from a common source. Their dynamics are independent. That creates the core contradiction. If the two comets have no dynamical relationship, why do they appear so similar now? There are only a few broad categories of explanation. The simplest is convergent physics. Different objects behaving similarly because the same physical rules can produce similar visible outcomes under certain conditions. Another possibility is that the resemblance is exaggerated by viewing geometry or data processing, turning superficial similarity into something that looks deeper than it is. More dramatic ideas, like a shared origin despite the orbital mismatch, have to clear a very high evidential bar because the orbital energy difference between bound and unbound objects is enormous. A normal fragmentation event cannot produce one fragment on a hyperbolic orbit and another on a long closed ellipse without an extreme and highly improbable sequence of gravitational events. At this stage, the honest position is that the resemblance is real in images, but its meaning is not established. What we do know is that two objects with radically different origins are showing comparable morphological features at the same point in time, while positioned in a near-symmetrical configuration around Earth's orbital neighbourhood. That alone makes this worth close monitoring. The only way forward is to move from impression to measurement. Compare high-quality imaging, collect spectra for SWAN, track changes in both comets over the coming weeks, and test each hypothesis against what the data actually shows. By the end of this investigation, we'll be able to say whether we're witnessing a rare natural overlap, a projection illusion amplified by processing, or something genuinely unexpected about how comets can behave. For now, the key fact stands. The orbital mechanics say these comets should have nothing to do with each other. The sky's showing us something that looks connected anyway. That tension is exactly where the real mystery begins. To make sense of what's happening, the first thing we have to lock down is the orbital math. Images can mislead, narratives can drift, but an orbit is an orbit. It tells you, without emotion, whether two objects could plausibly share a history. For 3I Atlas, the numbers are straightforward. Its path is hyperbolic, with eccentricity greater than 1. That means it isn't gravitationally bound to the Sun. It came in from interstellar space at high speed, will swing through the inner solar system once, reach perihelion on October 30th, 2025, and then head back out into the galaxy. There is no long loop, no return. It is a one-time visitor. Comet C 2025 R2 SWAN is the opposite case. Its eccentricity is about 0.994. That's extremely close to 1, but still less than 1, which makes it a bound solar system comet on a long closed ellipse. Most of its life is spent thousands of astronomical units away, in the outer dark where the Oort cloud begins. Its orbital period is on the order of centuries or millennia. This is not a traveller passing through. It is a native object making a rare return. Even their orbital planes diverge. You can picture the solar system as a flat disk, the ecliptic plane, where most planets and many comets move. SWAN follows a trajectory closer to that plane, typical for long-period comets. 3I Atlas comes in on a steeper, less aligned approach, again typical for interstellar visitors. If you integrate their orbits backward in time, they never converge into a shared corridor of space. There is no plausible fragmentation event that produces one interstellar hyperbolic orbit and one bound Oort cloud ellipse. The energy gap between those two states is enormous. Normal comet breakups don't supply anything close to the velocity change needed to flip a fragment from bound to unbound or vice versa. So orbital mechanics draw a clean boundary. These objects are not siblings. They are not fragments of a common parent. They do not come from the same dynamical family. Whatever similarity we think we see in their tails, it does not come from a shared origin. That is the puzzle in its most disciplined form. Two unrelated comets with opposite dynamical histories are showing what looks like similar morphology at the same time. Now we have to be careful. A comet's appearance is not a simple arrow pointing to its cause. What you see is a projection of a three-dimensional plasma and dust system into a two-dimensional image, filtered through Earth's atmosphere, telescope optics, and processing choices. View the same comet from a new angle or at a different phase of activity, and it can look like a different object. Textbooks say comet tails point away from the Sun. That rule is broadly true, but real comets are complicated. They usually have at least two tails. A dust tail, made of solid grains pushed by sunlight, is broad and often curved. An ion tail, made of gas that has been ionized by ultraviolet light, is swept into a straighter line by the solar wind. Add rotating jets from the nucleus, variable outgassing, and the fact that dust grains of different sizes respond differently to radiation pressure. And you get a system that can create unexpected shapes. 3I SWAN Atlas is being imaged by professional observatories and by high-level amateurs. In high-resolution data, the coma around the nucleus shows multiple jets. Those jets rotate with the comet's spin, turning on and off as active regions face the sun. From one viewing angle, they can look sunward, even if the material is actually moving outward on a curved trajectory. In other words, sunward facing in an image does not automatically mean sunward motion in space. SWAN is newer to the inner solar system and to our instruments. It was flagged only in September 2025, so most current imagery is from surveys and amateur telescopes. Those images are valuable but uneven. They often require heavy stacking and contrast, stretching to pull faint structure out of noise. That processing can exaggerate real features or create artifacts that look meaningful. Two observers using different pipelines on the same raw data can produce two different tail geometries. This doesn't mean the resemblance is fake. It means we can't treat visual similarity as proof of anything until we compare like with like. So the right question becomes, are these comets genuinely producing similar physical structures, or are we seeing different structures that only appear similar because of geometry and processing? Those are radically different scenarios, and the data needed to separate them is not optional. The next line of evidence is composition. We already have a strong chemical portrait of 3I Atlas because major observatories have observed it in multiple bands. Infrared spectroscopy shows a coma dominated by carbon dioxide rather than water. That is not typical for solar system comets, which are usually water-rich and show strong hydroxyl emission when water breaks apart under sunlight. 3I Atlas still has water vapor present, but the CO2 to H2O ratio is unusually high. Webb also detected carbon monoxide and a suite of organic molecules, complex carbon-bearing compounds. The simplest explanation is that this comet formed in a different stellar system and then spent a very long time in interstellar space. Galactic cosmic rays can process surface ices over millions of years, breaking apart water molecules, driving away hydrogen, and leaving a crust enriched in CO2 and organic residues. When the object enters the inner solar system, those irradiated outer layers heat up and sublimate first, shaping what we detect. Polarimetric observations deepen the oddity. The way 3I Atlas polarizes reflected light suggests dust grains with unusual size distributions or compositions, possibly organic-rich aggregates. There are also ultraviolet detections of hydroxyl emission at distances greater than 3 AU from the Sun, implying sustained activity where most comets are already quiet. Put together, 3I Atlas looks like an interstellar comet that has been chemically and physically altered by its long exposure beyond any heliosphere. For SWAN, we don't yet have that kind of chemical data in the public record. Without spectroscopy, we don't know whether it is a typical water-rich Oort cloud object or something much stranger. That gap matters because chemistry is the tiebreaker. Two objects can look alike for different reasons, but their spectra will tell you whether they share the same volatile inventory, isotopic ratios, and dust properties. If SWAN turns out ordinary in composition, then the resemblance is almost certainly coincidence driven by convergent physics plus viewing geometry. If SWAN shows the same CO2 dominance and similar organic fingerprints, then we have to explain how a solar system native acquired interstellar-style chemistry. That would be genuinely unexpected and would force a deeper investigation. Right now, we're stuck between those outcomes because the decisive measurements haven't been made. So what do we do with this today? We lay out the hypotheses in a way that can be tested fast. One possibility is simple convergence. Two comets, different origins, same sun, same solar wind, same radiation pressure, and the same basic physics of rotating jets and dust sorting. Under certain conditions, those ingredients can yield similar projected shapes. This hypothesis predicts no chemical match once SWAN is observed properly, and it predicts that the resemblance will fade as their geometry changes over the next weeks. A second possibility is a shared progenitor or fragmentation event far in the past. It sounds neat, but the orbital energy mismatch makes it nearly impossible. Normal fragment velocities are meters per second, not kilometers per second. To make this work, you would need an extremely rare history involving fragmentation during a gravity assist that captured one piece and ejected another. It isn't forbidden by physics, but it is statistically brutal, and it predicts we should find more fragments or a meteoroid stream. None are known so far. A third possibility is that the resemblance is overstated by processing and social amplification. Dramatic images travel faster than raw data. Once a visual narrative takes hold, people look for confirming frames and tune their processing to highlight similar features. This hypothesis predicts that the similarity weakens when you compare calibrated professional data with standardized reductions. And finally, there is the intentional or engineered idea that gets whispered online. The only responsible way to treat this is as a null check. Define what artificial activity would look like, then see if any of those signatures exist. You would expect non-gravitational accelerations that can't be explained by outgassing, narrow-band radio emissions, or repeating synchronized behavior that exceeds natural variability. Right now, there is no credible evidence for any of that. Both objects behave like comets. One is chemically exotic in ways consistent with interstellar processing. The other is still an open chemical question. So the mystery is real, but its meaning is not settled. The sky is giving us a visually striking coincidence. The orbits say it should be a coincidence. Chemistry will decide whether it stays that way. Science isn't about picking the most exciting explanation. It's about listing the plausible ones, asking what each would predict, and then checking those predictions against real measurements. With 3I Atlas and Comet SWAN, the resemblance people are talking about can be organized into a small decision set. Some explanations are ordinary, some are strained, and a few sit right at the boundary of what the data can justify. The value of laying them out is not that they are equally likely. The value is that each one can be tested, and most can be eliminated quickly. Start with the simplest option: convergent physics plus coincidence. Two comets can look similar even if they are unrelated because the same external environment is acting on both. Sunlight pushes on dust through radiation pressure, and that pressure sorts grains by size in the same way anywhere in the inner solar system. The solar wind drags ionized gas into straight iron tails in the same way anywhere in the inner solar system. A rotating nucleus with localized active vents produces jets and curved fans in the same way anywhere. If viewing geometry happens to line up just right, different comets can project into surprisingly similar shapes on the sky. This explanation makes clear predictions. First, SWAN's chemistry should look like a normal long-period solar system comet. In optical spectra, we should see strong water products, especially OH emission, because H2O dominates most native comet Comet. We should also see standard minor species such as CN, C2 and C3 at typical ratios. In infrared, CO and CO2 may be present, but they should not dominate the coma the way they do in 3I Atlas. Isotopic ratios should fall in the Oort cloud envelope rather than the interstellar processed envelope. Second, the visual similarity should be temporary. As Earth's line of sight changes, and as each comet responds to its own rotation and thermal history, their tails and jets should drift apart morphologically. If the likeness is mainly a projection effect, the resemblance will fade on its own as geometry evolves. Third, when you compare this pair to the full catalogue of comets, this kind of overlap should not be vanishingly rare. With thousands of comets observed and many combinations of jet angles and grain sizes, a few accidental lookalikes are expected. The second option is a shared origin through fragmentation. This idea says both comets are pieces of a larger progenitor that broke apart long ago. One fragment stayed on a hyperbolic interstellar trajectory and is now passing through as 3I Atlas. Another fragment somehow lost enough energy to become bound to the Sun and is returning as SWAN. It's a neat story, but it runs into hard dynamics. To turn an interstellar fragment into a bound solar system comet, you must remove an enormous amount of kinetic energy. Typical breakup velocities are meters per second. The energy gap between hyperbolic escape and a long elliptical orbit is many orders of magnitude larger. The only natural bridge would be a very rare sequence of gravitational encounters, most likely involving close multi-stage passes by giant planets that just happen to capture one fragment while leaving another unbound. This is not impossible in principle, but it is a narrow path. Because it is narrow, fragmentation makes strong predictions. The key one is chemistry. If SWAN and 3I Atlas are siblings, SWAN should share the interstellar fingerprints, an unusually high CO2 to H2O ratio, comparable CO levels, and a similar suite of organic lines. If cosmic ray processing shaped the surface of the progenitor in interstellar space, both fragments should carry that signature. We would also expect collateral debris. Fragmentation usually produces more than two pieces, plus dust trails that can become meteoroid streams. If Earth ever intersected those streams, we might see meteor activity tied to the parent orbit. If we find neither matching chemistry nor any debris evidence, fragmentation collapses. The third option is a common external natural trigger. The solar system is an active plasma environment. A coronal mass ejection or a shift in solar wind pressure can restructure ion tails quickly. A burst of solar ultraviolet can alter photochemistry and brighten Comet. If a solar disturbance hits two comets that are already close to a thermal threshold, both could respond with outbursts, fragmentation, or sudden tail reorientation within the same time window. In that case, the comets are not connected to each other, they're connected to the same driver. This explanation predicts tight timing. If the same solar event is responsible, light curves should show correlated changes after accounting for propagation delays of the solar wind. Ion tails should kink or brighten in ways that line up with measured solar activity. This is good news scientifically because solar conditions are tracked continuously. If there is no relevant solar event corresponding to the changes reported in both comets, the trigger explanation weakens sharply. The fourth option is observational bias and image processing artifacts. This isn't a conspiracy idea, it's a standard warning in comet work. Comet are faint, and pulling structure out of them requires stacking, point spread function correction, background subtraction, and contrast stretching. Those tools are legitimate, but they also change what the eye sees. A broad, low-contrast dust fan can look like a sharp sunward tail after aggressive stretching. A background gradient can turn into an apparent gap. Once a dramatic frame circulates online, other observers may, even without realizing it, tune their processing to emphasize what looks similar, because that's what the conversation is rewarding. If processing bias is the main source of the resemblance, the similarity will not survive careful cross-checks. A real physical feature should appear across different telescopes, different filters, and independent reduction pipelines with documented steps. An artifact will show up inconsistently or only under heavy manipulation. That's why raw frames and clear methodology matter more than polished social media images in a case like this. Notice what is not part of a responsible decision tree right now: any confident claim of deliberate control. Science does not treat that as a live hypothesis until there are specific, measurable signatures that natural models cannot reproduce. In practice, that means something like a persistent non-gravitational acceleration with no plausible outgassing budget or emissions that sit outside known molecular bands. At the moment, neither comet shows that kind of evidence. Both behave like comets within observational uncertainty, so engineered explanations have no footing. So the way forward is straightforward. Get spectroscopy of SWAN while it remains bright enough for good signal to noise, ideally in both optical and infrared, so we can measure water products, CO2, CO, and organic traces in the same framework used for 3i Atlas. Build light curves for both comets with standardized filters and accurate timestamps, so any correlated outbursts or divergences can be tested statistically rather than guessed visually. Keep collecting high-quality multi-filter imaging, but with transparent reductions, to watch whether the resemblance persists under changing geometry. And keep refining orbit solutions with realistic models for non-gravitational forces, so any unexpected thrust terms can be separated from ordinary jet physics. Once those measurements exist, the outcome is not ambiguous. If SWAN's chemistry is normal and the shapes drift apart, convergent physics and coincidence win. If SWAN's chemistry matches 3i Atlas in a deep way, fragmentation or capture becomes worth serious modelling despite its dynamical difficulty. If both comets shift in lockstep with a documented solar disturbance, the external trigger idea rises. If the likeness fades under standardized reductions, processing bias explains most of the drama. That's the disciplined posture. Right now we have a real visual overlap and an orbital separation that says it should be an overlap with no shared history. The job is to see which explanation survives when the decisive data arrives. Until then, every confident story is just a placeholder. To understand whether the resemblance between 3I, Atlas and SWAN is meaningful or superficial, we have to step beyond first impressions and look at how comets actually work on the inside. A comet's appearance, its coma, jets, and tail, is not a direct photograph of its nucleus. It's a reaction. The visible structure is shaped by solar heating, volatile chemistry, the nucleus's rotation, the distribution of vents on its surface, and the grain sizes of dust escaping into space. Two very different nuclei can produce similar visible patterns if the external conditions line up in the right way. This is why morphology alone can mislead. A sunward feature is not always a physical jet aimed at the sun. Sometimes it's a curved dust arc produced by an active region that sweeps through sunlight as the nucleus rotates. Sometimes it's a projection effect, a tail that is actually angled away from the sun but appears shifted in our line of sight. Sometimes it's a processing artifact. The sky is three-dimensional. Images are not. So before digging deeper, we need to map the physics that can make two unrelated comets appear similar. When sunlight hits a comet, different ices sublimate at different distances. Water ice becomes active around 3 AU. Carbon dioxide and carbon monoxide can drive activity much farther out. That matters because 3I Atlas appears to be CO2 rich, making it active at distances where many comets are still quiet. SWAN, on the other hand, might be water-dominated, but without spectroscopy, we don't yet know its volatile hierarchy. If both comets have at least one major vent that becomes active under similar solar conditions, they can develop jets with similar apparent geometry despite having completely different compositions and histories. Dust plays a second role. Small grains are pushed strongly by sunlight. Larger grains follow curved trajectories determined by both jet direction and radiation pressure. If two comets happen to be producing similar grain distributions, say a dominance of medium-sized grains, then their dust fans can project into similar shapes in processed images even if the underlying activity patterns are different. This is convergent behavior, and it doesn't require anything unusual. Rotation adds a third ingredient. If both comets have rotation periods that expose their active vents to sunlight at similar angles relative to Earth, their jets can appear to point in roughly the same direction from our perspective. This can create the illusion of coordinated activity when nothing of the sort is happening. Nucleus rotation rates vary widely among comets, but jet visibility depends on when the active area faces sunlight and where Earth sits relative to that orientation. In other words, geometry alone can make unrelated comets look related. But to be fair, convergent morphology is only half of the story. The other half is what is genuinely surprising about the timing. SWAN and 3I Atlas reached high visibility at nearly the same epoch, showed similar sunward-facing structures within weeks of each other, and did so while positioned nearly opposite each other along Earth's orbital plane. This is what pushes the resemblance from possible coincidence into worth investigating. This is also where solar wind conditions matter. The solar wind is not constant. Its density, speed, and magnetic polarity change as the sun rotates and as coronal mass ejections pass through the inner solar system. Ion tails respond quickly to these changes. If a solar disturbance sweeps across the ecliptic, multiple comets can show synchronized changes kinks in their ion tails, brightening in their comae, or reorientation of dust structures. It's possible that both comets responded to the same solar wind transition, and that the similarity is environmental rather than internal. So the next step is to bring solar data into the picture. During the period when the similarity was first reported, space weather monitors detected moderate shifts in solar wind density and field direction. That does not prove a causal link, but it does mean a shared external influence remains an open explanation. Now let's look at the more subtle piece: jet physics. Comets are not uniformly active. Most of their surface is inert, covered in dust or crusted ice. Activity often comes from a handful of vents, sometimes only one or two. If two comets each have a dominant vent, and both vents happen to be oriented at similar angles when illuminated, their visible jets can resemble each other closely. This is called single-source dominance. It is not common, but it is not rare either. Many comets exhibit a single major jet that defines their morphology for weeks. SWAN's early images suggest one strong sunward-facing feature and a fainter dust fan offset to the south. 3I Atlas shows a similar pattern: a bright, stable jet and a broader secondary flow. That does not mean they share a physical cause. It means they might both be in a phase where one vent dominates. If SWAN later develops more jets as it warms, its resemblance to 3I Atlas will weaken. If it doesn't, the shape may remain similar for purely physical and statistical reasons. Spectroscopy will decide whether this is coincidence or convergence. If SWAN is water-dominated, its OH lines should surge as it approaches perihelion. If CO2 drives its activity, its CO2 band will appear in infrared. This is where the comparison to 3I Atlas becomes decisive. The interstellar object already shows a chemical signature outside the solar system norm. If SWAN does not match that signature, the morphological overlap is almost certainly coincidental. If SWAN does match it, we have a real anomaly: two objects with similar chemistry but incompatible orbits. Now shift to tail structure. What appears to be a sunward tail may actually be a forward scattering dust enhancement. When dust grains sit at the correct angle relative to the sun and observer, they brighten dramatically due to a phenomenon called forward scattering. Many comets display this when Earth passes through a specific geometry relative to the dust fan. In images, it looks like a sunward plume, even though the dust is actually flowing away from the nucleus. Both comets passed through geometries where forward scattering is high. That alone can exaggerate similarities between their dust structures. In plain terms, The resemblance currently seen in images can emerge naturally from the physics of dust, light scattering, jet dominance, and viewing angle. But we also have to consider the more unusual hypothesis honestly. What if SWAN is chemically strange? It is rare, but not impossible, for solar system comets to exhibit interstellar-like chemistry. Some Oort cloud bodies formed near the Sun and were scattered outward early in solar system history. Others may have been influenced by nearby supernovae or migrated through chemically unusual regions in the young disk. It is conceivable, though speculative, that SWAN came from a formation environment different from that of most Oort cloud comets and retained a volatile mix that mimics interstellar chemistry. This hypothesis predicts that SWAN's spectra will diverge from typical solar system envelopes. If that happens, then we're not looking at coincidence. We're looking at an unexpected bridge between solar system and interstellar comet chemistry, which would reshape our understanding of how volatile reservoirs form and evolve. What we cannot do is jump to claims of connection or intent. The observational record does not support that. Their orbital histories don't intersect. Their dynamics contradict any shared origin, and no data currently suggests coordinated behavior beyond what can emerge from standard physics. Still, the coincidence is worth documenting carefully. Real patterns and fake patterns often look similar at first glance. The separation comes from data, not intuition. When the spectroscopy of SWAN is taken, when its brightness curve is mapped, when its dust composition is analysed, the resemblance will either collapse into coincidence or harden into a genuine anomaly. Until then, the responsible posture is simple. The similarity is real in images, but its cause is undetermined. Morphology alone cannot reveal origin. Only chemistry and time evolution can. When two comets appear similar, the next question isn't just how they look now, but how their behavior evolves over time. Comet morphology is not static. It changes predictably as the comet approaches the Sun, rotates and sheds material. This evolution is one of the strongest diagnostic tools we have. If 3I Atlas and SWAN are similar for a meaningful physical reason, their behavior should evolve in ways that reflect a shared underlying driver. If the similarity is coincidental, their paths will diverge naturally as each responds to its own internal structure. This is why time evolution becomes central. Morphology has patterns. Jet activity rises and falls. Dust fans broaden or narrow. Ion tails straighten or kink. These patterns depend on the nucleus's rotation, volatile composition, thermal history, and geometry. By watching how each comet changes week by week, we can test whether their resemblance runs deeper than appearance. Let's begin with the behavior expected from a normal long-period comet like SWAN. As it approaches the Sun, the first volatiles to sublimate are the supervolatiles, CO and CO2. When it reaches roughly 2 × 10⁻³ AU, water ice begins to dominate activity. This shift causes characteristic changes in the coma. OCH emission sharpens, the inner coma becomes denser, dust production increases, and the overall brightness curve steepens. The transition is gradual but robust across many comets. 3I Atlas doesn't follow this script perfectly. Its CO2-driven activity is unusually strong for its distance. Some interstellar comets behave this way. Borisov was active farther out than many solar system comets, but 3I Atlas sits at the more extreme end of that spectrum. If SWAN is water-dominated, then as it approaches perihelion, its volatile composition should diverge sharply from 3I Atlas, even if the current morphology looks similar. This is one of the decisive tests we are waiting for. Next, consider rotation. A rotating nucleus produces repeating patterns as active areas move in and out of sunlight. If both comets happen to have rotation periods that expose major vents at similar phase angles relative to Earth, their visible structures may appear synchronized despite having no relation. This rotational mimicry can persist for weeks, giving the illusion of coordinated motion. But this illusion breaks down once the phase geometry changes. As Earth and the comets move in their respective orbits, the angle between Earth, the Sun, and each nucleus shifts. If the similarity between 3I Atlas and SWAN is a projection coincidence, small cyclic changes in their rotation and sunlight angle will gradually pull their shapes apart. This is why repeated imaging matters. Matching snapshots don't tell a full story. Matching time series would be meaningful. A divergence in time series would support coincidence. Now let's bring in solar-wind interaction, which plays a larger role in comet behavior than many people realize. The solar wind isn't a smooth fluid. It's a dynamic stream of charged particles that can compress, kink, or even disconnect ion tails. A coronal mass ejection passing through the inner solar system can reshape multiple comet tails at once. If SWAN and 3I Atlas were influenced by the same solar wind front, their initial resemblances could be synchronized by accident. But solar wind effects don't stay aligned unless the objects are positioned similarly relative to the solar wind flow. Right now, the comets sit on nearly opposite sides of Earth's orbit. That means the solar wind strikes them from slightly different angles. Even if a single solar event caused their initial similarity, their responses should diverge as their relative angles change. Watching the evolution of their ion tails over the next solar rotation cycle will reveal whether their matching features are global responses or independent behaviors. Another crucial test is dust stratification. As comets warm, they release dust grains of different sizes. Larger grains move slowly and form a narrow backbone dust tail. Smaller grains accelerate under radiation pressure and fan out into broad arcs. The distribution depends on the comet's internal structure, volatile content, and jet pattern. Two comets that only look similar will start to show distinct stratification signatures as they eject dust at different rates and from different vent locations. Stratification evolves over days to weeks, giving us another time-based discriminator. If SWAN and 3I Atlas maintain similar dust fan widths, curvature, and stratification behavior over time, that would be unusual and would merit deeper scrutiny. If they separate quickly, coincidence gets reinforced. Next, we have brightness curves. These are powerful because they reflect the total activity of the comet and are less sensitive to image processing. A comet's brightness generally increases as R2 from solar illumination plus contributions from outgassing. Deviations from this curve can signal outbursts, fragmentation, or complex volatile layering. 3I Atlas already shows deviations tied to CO2 dominance. If SWAN is water-driven, its brightness curve should follow the classic water-ice sublimation pattern. Differences between their brightness curves will become sharper as both comets approach the Sun. If they stay similar beyond this point, we would have a genuine anomaly. If they diverge, as physics predicts they are behaving normally. Finally, there is spectral evolution, the most decisive long-term test. Even without early spectroscopy of SWAN, the evolution of its spectral lines over time will quickly clarify its volatile inventory. O growth signals water. CO and CO2 lines signal supervolatile dominance. Organic lines reveal dust composition and processing history. The rate at which these lines rise or fall will diverge naturally from 3I Atlas if SWAN is a standard Oort cloud comet. Spectral divergence would confirm that morphology was coincidence. Spectral similarity, especially in CO2 dominance, would challenge current natural models and force a deeper investigation. Now let's address the question floating around the internet. Could external influence or coordination be responsible? The scientific answer is, nothing in the current data supports that. Neither comet shows unexplained acceleration, anomalous emissions, or structural coherence beyond what jets and dust physics can produce. Their orbits contradict any shared past. Their dynamics contradict any linked mechanism. Morphology alone cannot overturn these constraints. But science also doesn't handwave coincidences. It tests them. And the way you test them is with time. Time reveals physics. Time breaks illusions. Time shows what sticks and what doesn't. If the resemblance between 3I Atlas and SWAN persists across multiple observation windows, multiple phase angles, changing solar wind conditions, and ongoing thermal evolution, then the similarity is not trivial. It would indicate that either SWAN is chemically unusual, or that comet morphology models need to expand. If the resemblance fades as expected, then the explanation is straightforward. Two unrelated objects happen to pass through similar morphological phases at the same moment. This is the core of responsible interpretation. Initial resemblance is not evidence. Evolution is. And this evolution has already begun. Over the next weeks, we'll see whether tail angles drift apart, whether brightness curves diverge, whether spectral signatures split, and whether dust stratification behaves differently. Each of these changes will tighten the story until only one explanation remains. For now, what we're observing is a coincidence strong enough to be interesting and constrained enough to be solvable. When people see two comets with similar tail geometry, the conversation usually jumps straight to appearance. But scientifically, the coma, the cloud of gas and dust around the nucleus, is where the real diagnostics live. The coma is a physical engine, not just a visual halo. Its density, structure, and chemistry reveal what the nucleus is doing under the surface. Once we compare coma behavior between 3I Atlas and SWAN, the resemblance becomes much easier to test objectively. A comet's coma is shaped by three major factors: volatile composition, which ices are sublimating outgassing rate, how vigorously those ices escape geometry, how the active regions aim their flows into space. These factors combine to create pressure fronts, dust fountains, shock boundaries, and density gradients. Even subtle differences produce noticeable changes as the comet moves. For 3I Atlas, we already have an unusually clear coma profile. Its activity is driven not by water, which turns on strongly closer to the Sun, but by carbon dioxide at large distances. CO2 sublimates at lower temperatures, allowing the comet to wake up early. That's one reason its coma has been extended and asymmetrical long before perihelion. It is behaving like an object that has spent millions of years outside any star's protective wind, allowing cosmic rays to restructure its surface chemistry. We also know that 3I Atlas has large dust aggregates, likely the result of interstellar processing. These grains respond sluggishly to solar radiation pressure, bending its dust fans in ways that differ from typical Oort cloud comets. SWAN, by contrast, is still chemically unresolved. All we have are brightness curves and early amateur images, which cannot determine which volatiles dominate. If SWAN is water-driven, its coma will thicken rapidly as it nears the Sun. If CO2 is significant, it will brighten earlier and display coma asymmetries similar to those of 3I Atlas. If CO plays a major role, the coma will extend even farther, producing a more diffuse outer envelope. This is why SWAN's first proper spectrum will be the moment when the resemblance rises or falls from speculation to evidence. Tails can look alike. Comae cannot hide their chemistry. To understand the coma better, let's separate its components. 1. The gas field. Gas in a comet's coma expands outwards roughly isotropically, but the Sun's influence breaks that symmetry. Photons ionize gas molecules, creating ions that the solar wind sweeps into a narrow, straight ion tail. Gas density also drops exponentially with distance, so gas structures are hardest to image unless the outgassing rate is high. 3I Atlas has already shown a gas field more extended than most comets at similar distances. That means its gas production is significant even when water sublimation should be weak. If SWAN does not show similar early gas activity, this will be the first place their behaviors diverge. 2. The dust field. Dust grains are heavier and slower than gas molecules. Their trajectories depend on grain size and composition. Large grains follow ballistic paths influenced by the nucleus's jets. Small grains are pushed strongly by sunlight. Similar dust structures can arise when two comets release dust grains within the same size regime. But grain size is tightly tied to volatile chemistry. CO2-driven activity tends to release coarser grains. Water-driven activity produces more fine dust and small particles. If SWAN is water-dominated, its dust field will diverge sharply from 3I Atlas as it becomes more active. Dust arcs will broaden faster, tail curvature will increase, and forward scattering enhancement will change shape. If SWAN instead releases coarse grains like 3I Atlas, that becomes a real anomaly worth noting. 3. Jet structure jets are the fingerprints of a comet's rotation and surface layout. They reveal how many vents exist and which are dominant. 3I Atlas appears to have one major vent controlling most of its visible morphology. This single vent dominance produces clean, stable fan patterns. If SWAN has multiple vents, its coma will become complex quickly as rotation exposes different areas. If SWAN has a single dominant vent like 3I Atlas, the resemblance could persist, but the cause would still be natural. 4. The inner coma boundary. The inner coma is where sunlight first breaks apart molecules, creating parent and daughter species with characteristic emission lines. It is also where jets collide with previously emitted gas, forming arcs and density waves. The shape of the inner coma is highly sensitive to nucleus size and activity. 3I Atlas has shown a surprisingly stable inner boundary. If SWAN shows the same stability, despite a different orbit, rotation state, and solar distance, that would be unusual. This brings us to the key question. What does the resemblance actually imply? Not connection, not intent, not shared history. It implies shared constraints. Physics places limits on how comets can look. Many comets, despite vast differences in origin, pass through phases where their morphology converges. When their rotation rate, active vents, grain sizes, and solar geometry align, they can appear surprisingly similar. But resembling each other briefly does not make them physically related. Now let's address the deeper, more measured interpretation. What if SWAN's coma turns out to be chemically exotic? There are rare Oort cloud objects whose volatile profiles look nothing like typical solar system comets. Some formed closer to the Sun and were ejected early. Some formed farther out than the traditional Oort cloud model predicts. Some carry organic-rich mantles shaped by UV bombardment or nearby stellar events. In such a case, SWAN could mimic the chemistry of 3I Atlas without being interstellar. This scenario predicts a high CO2 to H2O ratio, strong CO emissions, organic signatures above solar system norms, dust grains skewed toward larger sizes, early activity far from the Sun. If SWAN shows these traits, the resemblance gains legitimate scientific weight, not because the comets are connected, but because SWAN itself would be scientifically unusual. And that raises an elegant possibility. Maybe we're not seeing a connection at all. Maybe we're seeing two very different pathways to similar comet behavior. One object, 3I Atlas, brings interstellar chemistry shaped by millions of years in open space. The other SWAN may bring deep Oort cloud chemistry shaped by early solar system dynamics. Both pathways can converge into similar morphology under the same solar conditions. This is why the next observations are crucial. Over the coming days and weeks, SWAN's spectrum will clarify its origin. Its coma and jets will evolve, revealing its rotation, grain size, and volatile drivers. Its brightness curve will show whether water or CO2 dominates. Its dust tail will develop stratification that can be compared directly to 3I Atlas. If the similarity fades, coincidence wins. If it strengthens, the case becomes a multi-layer cometary puzzle. What we're witnessing isn't a mystery begging for a dramatic conclusion. It's an opportunity to watch how two very different comets evolve under similar external forces. The resemblance will either collapse naturally or reveal something new about how comets behave when chemistry, solar heating, and geometry align just right. This is where the real story lies, not in speculation, but in letting physics reveal itself through time. As both comets move deeper into the inner solar system, the most important thing isn't how they looked on the day the resemblance went viral. It's how they behave when the solar energy rises, the outgassing intensifies, and the coma begins to reorganize itself under real thermal stress. This is the moment when illusions fall apart and real physics takes over. Early similarities matter far less than the patterns that emerge when each comet is forced to reveal what it's made of. Every comet, no matter its origin, eventually moves into a phase where its internal structure becomes visible in the way the coma thickens, breaks, tilts, or stabilizes. Water begins to dominate activity closer to the Sun. Dust grains separate into different layers according to size. The nucleus rotation starts imprinting repeating signatures on the jets. And the inner coma boundary either holds its shape or fractures into arcs and waves. This transition exposes the physical truth behind a comet's appearance far more clearly than any static image ever could. For 3I Atlas, that truth is already emerging. Its coma remains unusually coherent, with a dominant jet that holds its orientation even as the comet rotates and as sunlight grows stronger. A single source appears to be controlling most of its visible structure, something that doesn't contradict natural physics, but does place it on the unusual end of comet behavior. Dust grains are still larger than average, the gas field stays extended, and the CO2-driven activity hasn't tapered off. Everything about its inner workings suggests an object shaped by long interstellar exposure, rather than the thermal cycling common in solar system comets. SWAN is still an open question. Its coma is beginning to brighten, but without spectral lines, we still don't know which volatile is in charge. Its dust behavior is ambiguous. The forward scattering plume that caused so many comparisons could be the natural consequence of a single active region, or the early signal of a volatile mix that doesn't match most Oort cloud comets. The more SWAN warms, the more its nature will surface. A water-dominated coma becomes dense and structured as it approaches perihelion. A CO2 or CO-driven coma behaves more loosely, with broader envelopes and more stable jets. What happens next is where the resemblance will either dissolve or harden. If SWAN suddenly thickens its coma the way water comets usually do, the similarity will fade quickly. Its tail will broaden, its inner boundary will shift, and its dust field will stratify differently from 3I Atlas, because water-dominated activity produces a completely different internal rhythm. If SWAN instead maintains a single dominant jet, releases coarse grains, and shows early gas activity that doesn't align with a water curve, then the resemblance moves from coincidence to genuine scientific curiosity. Not because the comets are connected, orbital mechanics still rules that out, but because SWAN itself would then be an unusual object worth deeper investigation. Solar wind behavior is the next filter. The solar wind reshapes ion tails in real time, and because the comets sit on opposite sides of Earth's orbit, they're now being hit at slightly different angles. If their ion tails respond differently to the same solar wind rotation, that's another sign their internal conditions aren't alike. If their ion tails kink or brighten at nearly the same moment in spite of the geometry difference, then something external is synchronizing their behavior. Not in an exotic sense, solar disturbances have done this before, but in a way that narrows the explanation space. Brightness is another quiet but decisive clue. Each comet's light curve reflects its true level of activity, not just how processed images make it look. A CO2-driven comet brightens steadily and often earlier than a water-dominated one. A water comet surges more dramatically closer to the Sun if SWAN and 3I Atlas begin to diverge sharply in brightness behavior, and it is likely they will. That will tell us their resemblance is surface level. If they track each other more closely than expected, then the case becomes more interesting, because brightness curves are difficult to fake with geometry alone. All of these changes coma structure, tail angle, gas density, dust stratification, ion tail response, and brightness evolution tend to amplify differences rather than similarities. Early in a comet's approach, physics creates convergences. Later, physics pulls everything apart. Watching that divergence is one of the most reliable ways to tell whether two comets are behaving similarly for a real reason or for a temporary geometric one. And now we reach the core idea. The resemblance never needed to imply connection. The solar system is full of physical coincidences because it is full of repeated patterns. Jets recur. Dust behaves predictably. Projection effects line up. Solar wind fronts sweep across multiple regions at once. A pair of comets developing similar shapes at the same time is unusual, but unusual doesn't automatically mean meaningful. What is meaningful is what happens when each comet crosses the threshold where the Sun stops being a distant influence and becomes a direct sculptor. The differences buried inside their nuclei volatile layers, dust reservoirs, structural weaknesses, rotational histories are about to matter much more than any geometry that made them look temporarily alike. One comet is interstellar, chemically processed by millions of years of radiation. The other is likely native, shaped by the solar system's early history. Those paths cannot stay disguised under strong solar forcing. They will diverge because they must. But there is always the possibility that SWAN won't behave the way most long-period comets do. Maybe its chemistry really is unusual. Maybe its primary vent remains dominant longer than expected. Maybe its dust grains are closer to the interstellar end of the spectrum than to the solar system end. If that happens, we won't be looking at a connection between two comets. We'll be looking at a rare case of two very different origins producing remarkably similar physics at the same time. That is the intrigue at the center of this story, not drama, not speculation, but the tension between what looks connected and what the orbits insist is separate. And tension is exactly where scientific discovery lives. Over the next phase, everything that was speculative will become measurable. The resemblance will resolve itself one way or the other, not through debate, but through the way each comet responds to sunlight, rotation, chemistry, and solar wind. No matter which way it breaks, the outcome is useful. If the likeness fades, we've witnessed an elegant example of convergent comet physics. If it persists, we've found a genuine anomaly that expands what we know about volatile behavior and coma formation. Either way, The sky is doing what it always does, revealing complexity we weren't expecting at the exact moment we're ready to study it properly. Once a comet gets close enough to the Sun, its surface no longer behaves quietly. Ice turns violent, pressure builds beneath crusted layers, vents awaken, shut down, or rupture. Jets shift direction as the rotation exposes new terrain. The coma inflates, fragments, reconnects, and sometimes tears itself apart. This phase where thermal stress becomes the dominant sculptor is the phase that reveals everything. If 3I Atlas and SWAN only look similar because of early distance geometry, this is where that illusion ends. If they share deeper physics, this is where it shows. The moment solar heating intensifies, a comet's identity emerges. Each nucleus has its own internal layering: compact ice, porous dust, organic crust, pockets of trapped gas, old fracture lines from previous passages, and regions untouched for millions of years. Solar energy interacts with that architecture in ways that are impossible to fake. A water-heavy comet thunders awake near the Sun. A CO2-heavy comet glows early and stays steady. A comet with a single dominant vent holds its shape longer. One with multiple vents becomes chaotic. These patterns are not cosmetic, they're structural fingerprints. For 3I Atlas, the structure already leans toward rare behavior. Its coma remains unnaturally stable for a body undergoing increasing solar stress. Instead of blooming into multiple jets, it continues to favor one source. Instead of fragmenting into dense fans at the inner boundary, it maintains a smooth, coherent envelope. Its dust population stays skewed toward coarse grains, resisting the dramatic widening typical of water-driven comets at this stage. Everything it does says, CO2 first, interstellar processed, slow to fracture. SWAN is entering the same regime, and this is where its true nature will step into the light. If water is its engine, it will soon betray the classic signatures: a thick inner coma, explosive brightness surges, widening dust arcs, rotational modulation creating complex overlapping fans. If CO2 is secretly its driver, its behavior will look calmer, more linear, more controlled, and surprisingly similar to 3I Atlas. If CO plays a measurable role, the coma will appear extremely diffuse, almost ghost-like, because Keough-driven expansion can dominate before the dust catches up. What matters now isn't whether they look similar, but whether they react similarly as solar heat climbs. Reaction cannot be imitated by geometry. It cannot be shaped by coincidence. It follows physics alone. The next few days and weeks will create natural tests without us having to do anything. As the comets rotate, their jet signatures will reveal whether they're truly alike or just superficially aligned. As solar wind intensifies and shifts, their ion tails will betray differences in gas density and field responsiveness. As solar irradiation carves deeper into their surfaces, hidden layers will break open or won't, and we'll see which nucleus is fragile and which is resilient. Brightness evolution is especially revealing now. A water-dominated comet often spikes abruptly as trapped pockets open, releasing bursts of dust and vapor. A CO2-heavy comet brightens more gradually, without the sharp peaks. If SWAN behaves in the jagged, erratic way typical of Oort cloud comets near the Sun, the resemblance with 3I Atlas ends here. If it instead rises with the same measured slope and avoids dramatic outbursts, the resemblance becomes more meaningful. Tail structure will shift too. Forward scattering plumes that appeared sunward earlier will either grow, fragment, or rotate depending on grain size and jet distribution. If SWAN suddenly shows a multi-layered dust profile while 3I Atlas maintains its narrower, more coherent fan, the story diverges. If both preserve a similar thickness, curvature, and directionality, then we're dealing with more than projection. Ion tails also respond immediately to solar wind patterns. A single coronal mass ejection can split or kink an ion tail in minutes. If both comets experience the same solar wind event from different sides of Earth's orbit, their ion tails will reveal whether the similarity is being driven externally or internally. If they respond differently, the illusion breaks. If they stay in sync despite geometry differences, the external driver hypothesis gains weight. But the most revealing feature, the one that will make or break the resemblance, is the inner coma boundary. This boundary marks where sublimated gas breaks apart and becomes visible. It isn't random. Its shape depends on volatile dominance, nuclear structure, and rotation. In water-driven comets, the inner boundary becomes turbulent and uneven near the Sun. In CO2-driven comets, it stays smoother and more symmetric. If SWAN's inner boundary destabilizes and 3I Atlas maintains its stability, their early resemblance will be explained as coincidence. If both stay coherent, we're looking at two comets with surprisingly aligned internal physics. It's important to keep one thing in mind. None of these outcomes imply any direct connection between the comets. Their orbits still forbid that. But resembling each other under increasing thermal stress is much more scientifically interesting than resembling each other far from the Sun. It means that two objects from very different origins share a surprisingly similar internal architecture, or that comet physics contains a pattern we have underestimated, and if SWAN undergoes fragmentation while 3I Atlas stays intact, the comparison ends immediately. Fragmentation is a chaotic, unmistakable event, driven by thermal cracking and internal pressure. An interstellar comet with hardened outer layers might resist these stresses longer. A solar system comet with deep fractures might break early. In that case, their structures will evolve along completely different paths. There's also the possibility that SWAN will reveal something entirely unexpected, an unusual volatile layer, a stable vent configuration, or a coma profile that doesn't match the classical models. If that happens, it doesn't link it to 3I Atlas. It simply means SWAN itself is far more interesting than it first appeared. So this chapter boils down to a single idea. Thermal evolution is the truth test. Early resemblance means nothing until sunlight forces the nuclei to reveal themselves. If they diverge, physics wins. If they converge, science gains a new phenomenon. Either way, the answer will not come from the way they looked at a distance. It will come from the way each object behaves now that the Sun is close enough to matter. This is where everything hidden becomes visible. As both comets move through their most active phase, the debate shifts from why do they look similar to what survives under pressure. Early resemblance can come from geometry, processing, or chance, but long-term behavior reveals something deeper. Whether each comet follows a predictable pattern tied to its origin, or whether SWAN begins to echo the interstellar strangeness that defines 3I Atlas. At this point, single snapshots no longer matter. What matters is consistency, what each comet does again and again as conditions change. A comet under strong solar forcing becomes a kind of experiment. The Sun applies the same inputs: heat, photons, solar wind, while each nucleus reveals its internal machinery in response. If the comets share only a superficial likeness, the shared illusion will start falling apart piece by piece. If the resemblance deepens, then we aren't looking at coincidence. We're seeing a physical pattern repeat across two unrelated objects, and that deserves attention. The first clues come from stability. 3I Atlas maintains a remarkably smooth structure even as the energy pouring into its surface increases. Its coma doesn't break into turbulent arcs. Its jets don't proliferate. Its tail doesn't scatter into multiple competing fans. Instead, it behaves with an almost disciplined coherence, as if its internal architecture channels energy through a single dominant source. That kind of stability isn't impossible, but it's uncommon for comets this close to the Sun, especially interstellar ones shaped by long radiation exposure. SWAN now enters the same stress regime, and this is where its real signature should emerge. Water-dominated comets become noisy under heat, rapid outbursts, jagged brightness spikes, chaotic jets. CO2-dominated comets stay more restrained, releasing gas before dust and maintaining smoother envelopes. CO-driven comets behave even more diffusely. As SWAN heats, it must choose one of these paths. It can't stay ambiguous forever. Heat forces a declaration. If SWAN suddenly becomes turbulent, while 3I Atlas stays coherent, the early resemblance dissolves entirely. If SWAN maintains coherence instead, the case takes a different turn. Not because the comets are linked they aren't, but because SWAN would be revealing a composition or structure more unusual than expected for an Oort cloud body. Another layer in this unfolding story is rotational behavior. As the nucleus spins, active regions pass in and out of sunlight, imprinting repeating signatures on the coma. In typical comets, these repeating patterns drift over time as new vents open or dust covers old ones. 3I Atlas shows stable repetition. If SWAN's jets start behaving like a rotating pattern with similar beats, that would be notable, not as proof of connection, but as an unusual coincidence in rotational dynamics. Brightness curves now become more revealing than imagery. A water-driven comet brightens unevenly, surging when buried pockets rupture. A CO2-driven comet brightens along a smoother, slower curve. The next rise in SWAN's brightness will say more than any photograph. If the increase is sharp, the resemblance ends here. If it follows a measured slope, the resemblance strengthens. Light is a quiet truth teller. Ion tails also enter a decisive phase. Solar wind structures, such as high-speed streams and magnetic sector boundaries, reshape ion tails in real time. If both comets respond differently to the same solar wind conditions, their physics diverge. If they respond nearly the same way despite sitting in slightly different solar wind geometries, then the similarity becomes harder to dismiss because ion tail behavior is sensitive to gas density and field coupling, not just line-of-sight projection. Dust remains the most telling piece of all. Grain size is a fingerprint of volatile chemistry. Water-driven activity releases finer dust, creating broad fans. CO2-driven activity releases coarser grains that resist radiation pressure and preserve narrow structures. If SWAN's dust begins to behave like classic water-dominated dust, widening and curving away, the match with 3I Atlas is over. If it stays coarse or behaves as though coarse grains dominate, then SWAN is not a typical Oort comet, and that makes the resemblance scientifically interesting, even without any connection between the two. The important thing is that none of this can be faked by geometry. Once solar intensity rises and sublimation accelerates, each comet's internal configuration dictates its behavior. Geometry matters less. Processing matters less. Coincidence matters less. The sun becomes the filter that strips away projection and reveals what's real. People love dramatic explanations when two objects appear similar, but right now the data still say the resemblance doesn't imply a shared history. Their orbital mechanics contradict each other. Their formation zones contradict each other. Their dynamical lifetimes contradict each other. But the challenge is that the sky sometimes produces real coincidences, rare, striking, perfectly timed. The question now is whether this is one of them. If SWAN begins to diverge chaotic jets, thickening water coma, widening dust fans, then the resemblance becomes nothing more than a well-timed alignment amplified by early geometry. If SWAN keeps mirroring the restrained stability, coarse dust, and single-source dominance of 3I Atlas, then the resemblance indicates something worth investigating on SWAN's side. It would mean SWAN has a physical structure closer to the interstellar end of comet diversity than to the solar system end. That possibility is intriguing, not because it implies connection, but because it expands what we thought Oort cloud comets could be. It suggests the solar system may contain a few rare bodies with volatile architectures or dust compositions more in line with foreign objects. Not alien, just unusual. Not extraordinary, just undersampled. The next stage of observation will strip away the uncertainty. As both comets enter a regime where heat forces their internal systems to reveal themselves fully, every ambiguity will collapse. Whether the resemblance dissolves or deepens, the outcome will be measurable. And as always, the universe does not explain itself through a single image. It explains itself through motion, through heat, through time. If the comets diverge, we close the book cleanly. Early similarity, late separation, no deeper meaning. If they converge, we open a new chapter 1 where two unrelated objects reveal similar physical responses under extreme conditions, hinting at comet behavior that our models haven't fully mapped yet. Either outcome is a discovery. As the comets continue their inbound paths, the conversation inevitably shifts toward the one filter that settles every ambiguous case in comet science: post-perihelion behavior. What a comet does after it survives its closest approach to the Sun is often more revealing than anything it does beforehand. Perihelion strips away illusions. It exposes weaknesses in the nucleus, reveals hidden layers of volatile ices, and forces every patch of the surface into a regime of extreme stress. No two comets pass through this unchanged. Their internal architecture, whatever it is, becomes impossible to hide. This is the final truth test for 3I, Atlas, and SWAN. If their resemblance was only a projection effect, or a coincidence triggered by early activity, perihelion will break the symmetry. If their resemblance is the result of deeper physical similarities, perihelion may reinforce the match instead of dissolving it. The physics here is simple. Solar heating increases sharply near perihelion, and comets react in predictable but distinctive ways. A water-heavy comet often experiences violent outbursts as subsurface pockets burst through the crust. It can shed layers, fracture visibly, or even split apart. Its dust production rises steeply, creating wide, chaotic fans. CO2-heavy and CO-dominated comets behave differently. They heat earlier, peak earlier, and their outgassing fades more smoothly as they exit the inner solar system. 3I Atlas is built for this test. Its interstellar processed surface has likely spent millions of years exposed to cosmic rays, hardening the outer layer into something more resistant than typical Oort cloud crust. If that's true, perihelion may not break it. It may simply intensify the one major vent that already defines its structure, deepening its single source morphology instead of chaotically reshaping it. That would be unusual, but consistent with its behavior so far. SWAN, by contrast, is a mystery box about to be opened. Its early morphology didn't tell us what volatile dominates. Its brightness pattern didn't settle the question of whether water or CO2 is driving it. Perihelion will. A water-driven nucleus will act loudly. Fragmentation risks rise sharply, jets multiply, brightness climbs unevenly. A CO2-driven nucleus will behave more quietly, more structurally stable, more like 3I Atlas, and if SWAN actually shows a Keoheavy profile, its post-perihelion coma may become extremely diffuse, revealing a volatile inventory closer to an interstellar object than a native solar system comet. This is why post-perihelion observation is more important than anything captured so far. The Sun now becomes the interrogator. The nucleus has no choice but to answer. Tail geometry also changes in a way that reveals identity. Before perihelion, forward scattering can enhance certain angles, making dust appear brighter or more aligned than it really is. After perihelion, that optical boost disappears, and the tail geometry settles into a more honest configuration. Differences in dust grain size, composition, and velocity become far clearer, because the tail no longer benefits from the optical tricks of inbound lighting. 3I Atlas is expected to maintain a narrow, coherent fan if coarse grains dominate. SWAN, if water-driven, should produce finer dust that widens and curves. If the two tails finally separate here, the early resemblance becomes clearly superficial. If they stay strangely aligned, if both tails preserve similar curvature and thickness, even without forward scattering, then the resemblance is rooted in real physics. Ion behavior reveals even more. After perihelion, the comet begins moving away from the Sun, and the ion tail's orientation becomes strongly tied to solar-wind interactions. A gas-heavy comet with large-scale outgassing produces a long, clear ion structure that reacts sharply to the solar wind. A comet whose tail was mostly dust-enhanced earlier will show much weaker ion activity. If 3I, Atlas and SWAN suddenly diverge in ion strength or responsiveness, the symmetry breaks. If they respond with the same sharpness, then the resemblance is not an accident of geometry, it's a reflection of similar gas-driven behavior. Rotation also reaches peak influence after perihelion. The nucleus has been heated unevenly. New vents may open, and pre-existing ones may shut down. Dust jets either multiply or stabilize. Repeating modulation in coma brightness becomes more obvious. 3I Atlas has shown remarkably stable rotation-linked features so far. If SWAN begins showing chaotic modulation while 3I Atlas continues with disciplined stability, the early resemblance splits cleanly. If SWAN mirrors 3I Atlas by showing a dominant repeating jet cycle, that would be highly unusual and worth paying attention to. Fragmentation is the sharpest dividing line. Many long-period comets fragment near perihelion due to internal pressures and thermal cracking. An interstellar processed object like 3I Atlas may remain intact. If SWAN fragments and 3I Atlas doesn't, the comparison ends on the spot. If both remain intact despite severe thermal stress, the symmetry becomes scientifically meaningful, not because it signals connection, but because it signals similar structural resilience, which is rare for two comets of unrelated origins. Brightness evolution after perihelion is also crucial. Comets typically dim quickly as their water source weakens, but CO2-driven and CO-driven comets fade more slowly and more evenly. If 3I Atlas dims along a smooth curve while SWAN shows classic water-driven drop-off, we close the resemblance chapter. If both fade along the same smoother curve, SWAN becomes a far more interesting object than originally expected. But the real test comes when the comets move back into deeper space. As cooling begins, their activity drops into a regime where only the strongest vents remain active. The morphology becomes simpler, the coma shrinks, and the underlying grain population emerges more clearly. After perihelion, the noise falls away. What remains is structural truth. This is where their identities should diverge definitively. Their origins demand it. Their orbital histories demand it. Their chemistry, once SWAN's is measured, will likely demand it too. And yet the possibility remains that SWAN may surprise us. Not because it is connected to 3I Atlas, but because comet diversity, especially in the outer solar system, may be broader than we assumed. If SWAN behaves like an interstellar object in terms of dust, gas, and stability, then we are not seeing a connection. We are seeing a category of comet that we haven't classified properly yet. This is how science expands, not by jumping to extraordinary explanations, but by letting persistent anomalies reshape the boundaries of our models. And perihelion is where the reshaping happens. Whether SWAN diverges or converges, this phase will produce one of the cleanest answers in the entire investigation. Comets cannot hide their identity under extreme heat. Their cores reveal themselves through fragmentation, jet behavior, coma density, dust physics, ion tail structure, brightness curves, and post-perihelion decay. These signatures don't care about appearance. They don't care about coincidence. They don't care about narrative. They only care about physics. By the time both objects clear perihelion, the resemblance will either have collapsed naturally or it will have transformed from a visual curiosity into a real scientific puzzle worth deeper exploration. And if the answer turns out to be simple coincidence, that's still a discovery, because it tells us how easily the sky can deceive us when we rely on snapshots instead of evolution. Either way, the sun is about to decide the outcome.